Welcome to session 1 of lesson 1. The first week was our lesson 0 to prepare us for this new curriculum and to model what it would look like in our classroom with some review skills from previous grade levels. Now we're moving into our 6th grade standards. So the first standard that we're going to deal with is going to be to find the area of two-dimensional shapes, such as triangles and rectangles, to also be able to look at the area of a parallelogram and other quadrilaterals. And we will eventually move into decomposing quadrilaterals so that we can decompose them into triangles and rectangles in order to find the area for our shapes. Today, in session 1 for lesson 1, we are going to be exploring the area of a parallelogram. We have talked about area before. We talked about the area of a rectangle. So when we're dealing with the area of a rectangle is shaped like this. When we want to find the area of that, we have said before that our area formula for a rectangle would be length times width. We have also talked about the space inside of this rectangle. That is the area. And that we can measure the area, or when we measure the area, we are measuring in square units. There are some that like to write this as units squared. Both ways are correct. So we're going to take a look at a problem. This problem says, Kenji and Alec are making paper kites for a kite fight. Kenji's kite is a rectangle and Alec's kite is a parallelogram that is not a rectangle. Each boy draws a model of his kite on grid paper. Does Alec's kite use more paper than Kenji's? So Kenji's kite is a rectangle. This is Kenji's kite and his model, which means that this is Alec with the parallelogram. And they want to know that looking at those models, does one use more paper than the other? So specifically, they're asking about Alec. Does Alec use more paper to make his kite? They are in different shapes. One thing I do want to point out is that when a shape is a shape, we don't want to manipulate it by trying to straighten it out. So we want to leave the parallelogram a parallelogram. We don't want to try to straighten out the sides. Then we would be changing our area. So we want to leave the shapes just as they are. And we want to find out how much space is inside of each of those shapes. So what could we do to find out how much space is inside of those shapes? How many square units are in each of those shapes? How could we figure that out for these two shapes? We can use square units. Inside of each of those shapes are small boxes, and those small boxes are each 1 unit. So we can count up the boxes in each. So that's what I want you to do on your paper in the try it box. You are going to count up the squares in Kenji's kite, and you're going to tell me how much area is in his kite. And then you're going to count up the squares in Alec's kite and tell me the area of his. Then decide, did Alec use more paper? So take a moment to pause the video and do this. So in taking a look at this, we want to count up the squares in each. So we would count going across, and we would find that that is 5 squares. 1, 2, 3, 4, 5. Then we would count going up, and we would find that we have 4 squares. A box that has a 5 by 4 array inside of it would be 4 times 5. So this would be 20 units squared. So Kenji's kite uses 20 units. Let's take a look at Alec's kite. You may have noticed that there are some places on this parallelogram where half of a box is used. What you need to do is you need to decide, going across, how many boxes, whole boxes, would be used. We have half of a box on the left and half of a box on the right. So that gives us 1. And then we count the boxes that are left. So we have 1, 2, 3, 4, plus our 2 halves. So we have 4 and 2 halves, which gives us 5. Then we want to count how many boxes tall. So how many rows do we have? So we start at the bottom row and we count all the way up to the top of the shape, to the very top row. So we would count that and we would say we have 1, 2, 3, 4 rows. So again, we have a 5 by 4. 5 times 4 is 20, and we have 20 units square. So now we know the answer to the question, does Alec use more paper than Kenji? Which brings us to the connected question. So here you are going to write the answer to that question. Does Alec use more kite paper than Kenji? And then you're going to explain how you know that. So take a moment to pause the video and do this. And we should have decided that no, Alec does not use more paper for his kite. And the reason why is that both models have the same area. So in order to cover that area, you need the same amount of paper. Let's take a look at number 2. It says, look ahead. The words length and width are often used to describe the dimensions of a rectangle. Let's take a minute to make a note of that. Dimensions of a rectangle. So if you have space, write this in the margin on your paper. The dimensions of a rectangle are length and width. That's what we use to find the area, length times width. Well, what we're going to look at is a parallelogram. So the dimensions of a rectangle are length and width. But when we're talking about the dimensions of a parallelogram, we're talking about base and height. So again, in the space in the margin, you're going to draw a parallelogram the best way that you can. And you're going to decide if dimensions of a rectangle, we can multiply the dimensions of a rectangle together to give us the area, length times width. Can we do the same with a parallelogram? Can we do base times height to find the area of a parallelogram? And hopefully you noticed from the problem with Kenji and Alec that that's exactly what we were doing. We were using the base and the height and multiplying them together to find the area. So again, make a note about this and how we find the area of a rectangle and a parallelogram, because that is what this lesson is all about, is figuring out how to find the area of a parallelogram. All right. If we're looking to find the height of a parallelogram, wherever the base is, so in this particular parallelogram, the base is here. To find the height, you start at the base and go all the way to the opposite side. I went a little further on my picture. But you go from the base to the opposite side. It's showing you in the second picture of the same parallelogram that if you wanted to, you could label the height outside of the parallelogram. So you would be imagining the base extended so that then you can find the height from that base all the way to the opposite side of the shape. So again, same parallelogram. We started inside of the parallelogram to find the height here. We start outside of the parallelogram to find the height in the second one. The height does not change, but there are different ways that you can find your height. So let's apply that to A and B on number 2. So they have told you where the base is for A, and you have to decide how many units long is this base. So take a moment to pause the video and decide how many units long, how many squares long is the base. Hopefully we noticed that this is 5 units, 4 whole units and 2 half units. Then we look at the height. Now they did not label the height for you because you can find it in different ways. As long as you start at the base and go all the way to the top of the shape on the opposite side, I shouldn't say to the top, as long as you start from the base and go to the opposite side, you are finding the height. So then we look at our height here and we see that it is 4 units. So the length of our height is 4 units. And we can take those two and multiply them together to find our area. So we can say 5 times 4, because that would be the base times the height. So 5 times 4 is 20, and we are talking about units squared. So 20 units squared. Then we take a look at B, and they have labeled the base of the parallelogram in B on this side of the shape. So we look again and we count the units for our base. We have 3 whole units and 2 partial units to give us a total of 4 units. Now we go back and we label the height. As long as you start from the base and go to the opposite side, you have found the height. We count up our units for our height, and we would find that it is 5 units. So again, we can multiply base times height, and we would have 5 times 4, which would give us a total of 20 units squared. So this is how we can find the area of a parallelogram. We choose the base, and then we measure from the base to the opposite side of the shape for our height, and we multiply those dimensions together. That brings us to the reflect question on number 3. What number 3 is asking you to do is to take a look back at this A part. And here's the base. And when I did the height earlier, I chose to start from this point and go all the way to the opposite side. Again, sorry, I went a little further than that. What this is asking you is if I change the point of where I have my height. So right now, there's a half a square and then a whole square, so I went half and 1 whole square over to find my height. Let's say that I chose a different way. Let's say that I chose to do that imaginary line and started here and imagined my base coming up, or imagined my height coming up here and then connecting over to the side. Does my height change by coming over here and measuring it from this side versus where I did on the opposite side earlier? So number 3 wants to know, just because you move over on the base, if you slide up or down on the base, does it change your height? So take a minute to answer that question and explain. And you can pause the video to do that. So the answer here is no, it does not change your height. Your height is going to stay the same as long as you start at the base and go to the opposite side. It doesn't matter if you measure the height there or here, but you just have to make sure you go all the way to the opposite side. Sorry, that line didn't cooperate very well. And go all the way up, okay? So as long as you start at the base and go all the way to the opposite side, then your height is not going to change. We did not do this page in the student pages. We did talk about area, and we talked about how it is the space inside of a two-dimensional shape. We talked about what area is not. Area is not volume. Volume would be the space inside of a three-dimensional shape. And then in class, we talked about how area is not the perimeter. So it's not the outside edge of the shape. It is strictly the inside of a two-dimensional shape. The next thing that you can look at is number 2 and number 3 for session 1, and you can answer those questions. There is an A and B part to question number 3. So answer those 2 questions on your own. And if you have questions for me about those, you are welcome to ask them and I will answer them. Just let me know that you have questions and I am here to help. I'm happy to help you. So just let me know what you need.